Okay, hi everyone. We have another episode of my Q&A about science and technology for kids and others. And I think we have a few saved up questions here. I noticed one here. The question was, when will we run out of scientific innovations? Is there a limit to technology? You know, there's a famous story that's told, I think from about 1900, about the person who was responsible for the patent office, which is the place, and this was one in the US, where people who've made new inventions register their inventions to make it clear that the inventions are theirs, so to speak. Anyway, this person said basically in about 1900, everything useful that could be invented has been invented. You know, we've got millions of patents that have been issued about inventions of all kinds of things. You know, everything that is useful that could be invented has been invented. Well, that was a bit weird in 1900. You know, there were the Wright brothers with their plane coming in a few years. There were cars that were just starting to exist. There was all kind of innovation in bicycles. There was refrigerators. Oh, and, you know, then coming another probably 40 years later were computers and everything computers have brought us. So that was kind of a short-sighted thing to say in 1900, was everything that can be invented has been invented. And I think there's a question, will we ever be able to say everything useful that can be invented has been invented? And I'm pretty sure the answer is no. I'm pretty sure that for reasons that are actually kind of reasons, almost mathematical reasons, there will never be a limit to what can be invented. So we have to think a little bit more carefully about what does it mean to have an invention. What it probably means is we're going to take something in the universe, something that it can be made out of physical components, you know, some metal that we mined somewhere, some gas that we can construct in whatever. We're going to take something made out of physical components that we find in the physical universe, and we're going to turn that into something that we find useful. So there's sort of two constraints there. What can you find in the physical universe? What can you make things in the physical universe do? And what things do we find useful? Now, you know, you could imagine if you led a very boring life, or what to me seems like a very boring life, and all you did all day was you just sat in one room and you maybe you grew some food and you did this and you did that and nothing much else happened. One could imagine that, well, you wouldn't really need, you know, many other things that to change. I'm reminded many years ago, I was at a dinner at this is kind of a silly story, but I was at a dinner at Oxford University, at a college in Oxford University, and the colleges in Oxford University, some of them are very old. The first ones came into existence, I think, in the 1200s, so 800 years ago now. And one of the people who was there was an old chap who worked in some subject that, as you know, the history of things that happened thousands of years ago, was in the kind of, oh, nothing really ever changes in this world. You know, the only thing that's really significant from modern technology in his world is that, you know, at the dinners that they have, the thing that you can kind of slide a tray across the table with a thing made of, you know, Teflon or whatever it is, some low friction thing, and that for him was sort of the only important feature of modern times as far as he was concerned. For most people, there's a lot more use of kind of the innovations that get made in the world. But to some extent, the innovations that are worth making are features of what we think is worth doing, so to speak. So then there's the question. So then you have to sort of start asking this question, what's possible in the physical world? What do we care about? So there are probably limits in the physical world to things we can do. For example, if we want to send a signal somewhere, there's probably a limit. We probably can't send a signal, probably can't make anything go faster than the speed of light. probably light is the thing that goes the fastest in our universe. Probably. We're not sure about that, but probably that's true. And so if we say, well, the thing we really, really want to do is make something which travels faster than light, sorry, the universe as the universe exists just doesn't make that possible for us. But if we start, even when it comes to something like that, even though we can't send a signal faster than light, there are all kinds of weird effects. There's a thing called quantum teleportation, which doesn't really quite send a signal, but it kind of sends something else at a certain speed. And a lot of the time when people say, oh, there's a physical limitation that makes such and such a thing impossible, there will turn out to be some, maybe not a direct way that you can solve the problem, but something where you're kind of finding a way to work around the problem. I mean, in a famous example of this about also sending signals was years ago, I remember people saying, if you want to communicate between computers, the fastest you'll possibly be able to communicate is 1,000 bits per second. 1,000, so if you were sending text or something, a single character in text is usually encoded in about 8 bits. So that means that, let's see if I can do my arithmetic properly, that the fastest you'd be able to send things is maybe 120 characters per second will be the fastest you could send any kind of computer data information. Okay, so if that was the case, we'd be out of luck sending movies to computer to computer and so on, because that's a vastly larger number of bits per second and so on. But and people had all these arguments. Oh, if you have these wires and these radio signals and things, you'll never be able to send things faster than this or that for practical, sort of physical reasons. But it turned out that there were all kinds of things where people said, oh, the rate at which there will be errors will be too high. But then people figured out how to make error correcting codes. Oh, there'll be bursts of noise and so on. Then people figured out how to sort of get around those. And in the end, you can send data of millions of bits per second, routinely done, through exactly the same sort of physical ingredients. But the exact details of how those bits are sent and what rules you have about whether a bit that is sent will always arrive before a bit that's sent after it and all those kinds of things, those rules have been relaxed a bit, because it turns out for the things we actually want to do, those don't matter much. So anyway, this question of what can you invent? What constraints are there in the physical world that limit inventions? I think the thing that actually has been a consequence of my project about fundamental physics recently is we've realized the incredibly close connection between sort of what happens in the physical world and what happens in computers. What happens when you're computing answers to things turns out to be essentially the same as what's happening in the physical world when the physical world has things happen in it. And also, a thing that's much more recent is a realization that what happens in, well, what's usually called meta-mathematics, a kind of generalized view of mathematics, is also the same. And it turns out that in these more abstract theories in computation and meta-mathematics, there are fundamental results that basically say there will be new things you can figure out. There will be no limit. Like in mathematics, you might say, just like you could say, all the inventions that have been made of devices and so on, might have already been made. Well, they haven't. You might say in mathematics, all the mathematical results that are worth establishing have already been established. But we can kind of show in a very theoretical way and very, very formal way, a very sort of definite way, that can never be the case. There's no limit. There's an infinite frontier. There are always more mathematical results that you can derive that you won't have derived before. So I think we can fairly say that there isn't a limit. And when you the kind of way to think about this is, let's see if there's a way to describe this. A lot of these questions come down to questions, well, given these rules for how a system works, is there a way to set the system up so that when the system is following those rules, it can do the following kind of thing? Okay, where the following kind of thing is something you want from it. You want it to generate some sequence of numbers. You want it to do this or that or the other. And you might say, well, gosh, given that thing I want, well, how would I know if I can get it? Well, one way to know you can get it is just to say, here's a way to use those rules to get what I want. Okay, you're done. You've proved that you can make that invention, so to speak. Okay, how would you prove you can't make that invention? Well, you'd have to say there is no way of setting up these rules and setting things up so that you can get this thing I want. But if you just start, imagine how you would show that. One thing you could do is you say, well, I'll just try all the possibilities and I'll just show that nothing works. It's like you try all the possible inventions to prove that it's not possible to make a such and such device. But the thing that goes wrong with that idea is that partly because of a thing I call computational irreducibility, which is sort of a fundamental fact that I've been a lot involved in working on, you pretty much are stuck just having to try all these possibilities. And if you can't say, well, it has to be the case that within the first trillion things I try, something will show up or it's never going to show up. If you don't know how long you'll have to go, how many things you'll have to try, how many different things you'll have to try before you find a thing that works, then you'll never be able to say for sure, oh, there's nothing that works. And that's kind of the formal version of this is related to this thing called Gödel's theorem in mathematics. It's related to a halting problem in theory of computation and various other kinds of things. But the basic end result is you never know you can't do something because you end up having to say, well, I could try all these possibilities, but there's no limit to how many possibilities I'd have to try before I find something that works. And given that, I can't say for sure that it doesn't work because I would have had to try an infinite number of possibilities to be able to say that. Let's see. There's a question here. There's a question from Sarah here. Is it possible to build a place without gravity? Well, so the gravity that we're most familiar with is you drop something on the earth and it falls to the ground. That's the general rule of gravity is that objects that have mass attract other objects. So for example, the earth, because there's a big mass, will attract other objects through the force of gravity. And so things that you drop will tend to move towards the earth. What does it mean to move towards the earth? In the end, partly because the earth is a sphere, it means that things will tend to move towards the center of the earth. Now, obviously, when they hit the ground, they don't go all the way to the center of the earth, but they're always moving in a direction that goes towards the center of the earth. Actually, that's not quite true. It turns out that the mass always produces gravity. But if you look in different places on the earth, you might think everything will always fall down towards the center of the earth. But actually, because there are things like mountains, for example, which have mass, if you drop something sort of to the side of a mountain, you can end up with a situation where the thing is turned a tiny bit towards the mountain. It's actually falling a little bit towards the mountain as well as falling towards the center of the earth. Actually, that story is a little bit trickier because of the way that mountains float on the mantle of the earth. And so there's some slight trickiness with that. But basically, what is it? I think it's about 1 in a million, roughly, I think, is you're going sort of to the side about 1/1,000,000th as much as you're going down when something falls on the earth. But in a first approximation, gravity on the earth works the way it does because the earth has a mass. And so anything gets attracted by gravity towards the earth and towards the center of the earth. Now, one of the things that can happen is if you are, okay, so how do you be in a place without gravity? Well, as you go further away from a thing that has mass, the amount of gravitational force that it exerts goes down. It goes down roughly like the inverse square. So 1 over the square of the distance. And it's roughly this. I mean, so that means if you're twice as far away, the force of gravity is 1/4 as much. If you're 3 times as far away, it's 1/9 as much. And roughly the way you can think of it is if you think about a sphere, for example, and it has a bunch of mass, and you just imagine that from that sphere, there are these little things going out in all directions that are trying to pull things in with gravity. And actually, there are real particles, they're called gravitons, that probably you can think of gravity as more or less being like this whole stream of gravitons is coming out from an object and going outwards. And every time, and a graviton can kind of pull on anything to get that thing to go closer to an object. Okay, so here's a thing to think about. If you have a certain number of gravitons, and they are, every graviton is going to exert a certain force on something. But the question is, as you go further away from the object, how many gravitons will actually reach you as you go further away from the object? So when you're right close to the object, let's say there were a million gravitons that came out in a tiny, tiny fraction of a second from that object that were going to produce a force on things around it. Okay, there are a million gravitons that are going out in all directions. Okay, if you are a certain distance away, and you have a certain size, what's the chance that in that moment, a graviton, let's say it's going in a straight line, will reach you? Well, that depends on, let's say there are a million gravitons, they're all going out, it's like a big hedgehog-like thing, everything's just going out in a straight line from the center. The question is, how many, if you are a certain distance away, how many of these gravitons will reach you? So let's say that you were right on the surface, you were something where one of these gravitons, you were a certain size, and on average, every zeptosecond or something, tiny fraction of a second, one graviton would reach you. Okay, now let's say that was the case for on the surface of the Earth, which is a certain size. Now you go further away, what you realize is the further away you are, the number of gravitons that go through a certain area will go down as the distance away goes up. And actually, if you know the math of this, if you have a sphere of radius r, the area of the surface of the sphere is 4 pi r squared. So that means that as you go a distance r away, any given size, the total area that these gravitons have to go through goes up like r squared. But if you are of a fixed size, the number of gravitons that will sort of go through you goes down like 1 over r squared. And that's basically why the force of gravity decreases like the inverse square of the distance. It's just because you're having these essentially gravitons just streaming out, but there are fewer and fewer of them that will reach you if you're a certain fixed size as the distance you are away goes up. Okay, so that means if you're far enough away from every massive object in the universe, there won't be much gravity. So if you were out between galaxies, things like that, there won't be much gravity. The main gravity you'll feel is gravity that's pulling you towards that galaxy. Now, if we really get tricky about it, it's a little bit more complicated because there may be a sort of thing like gravity that is associated just with the vacuum. And that's a complicated issue of physics. There's this thing called dark energy that might exist in the universe that's sort of a little bit like that. But in a first approximation, if you're far away from any known sort of massive objects, then you won't feel much gravity. So that's one way to be in a place without gravity. Another way of appearing to be in a place without gravity is if you're like in orbit around the Earth. So as I say, well, let me explain this way. Let's say you're in an elevator and you drop something in an elevator. The elevator's stationary, okay, you drop something, it'll just fall to the ground just like it ordinarily would. But let's say you're in the unfortunate position that the elevator is in free fall, that the elevator is no longer acting as an elevator with all its counterweights and all that kind of thing. The elevator is just dropping, right? It's just falling. Maybe you're doing some bungee jumping insanity or something like that, and you're just falling, or you're skydiving or something. Those things don't quite work that way because of air resistance. But in a first approximation, if you were just falling as fast as you could towards the Earth and you drop something as you're falling, well, then you won't see that thing fall to the ground, because in a sense, the ground in your elevator is falling as well. So relative to sort of the ground, the thing you drop won't seem to fall at all. It will seem to be weightless. And the same thing happens if you're in orbit, like in the International Space Station. It's the same situation. The International Space Station is always falling towards the Earth, but because it's going a certain speed sideways as well, by the time it would fall and go splat on the Earth, it's actually gone far enough sideways that instead of just going splat on the Earth, it just keeps going around the outside of the Earth. That's what happens when things are in orbit. And in that situation, things will appear to be weightless because, in a sense, the ground is falling as much as anything would fall. Okay, so another question might be, so I said that anything with mass attracts things gravitationally, and the same is true even with satellites. It's a very, very small effect, but if you have if you had two International Space Stations, they would have a small force of gravity that will tend to attract them together. It's a very small force, that's would eventually do that. But so one of the things that this kind of assumes is that everything has a positive mass, because the force of gravity is associated with the mass of an object. If something has a positive mass, it's going to attract everything. If it had a negative mass, well, then it would repel things. That's the way it would work. But one of the things that seems to be true about gravity is there are no negative mass objects in the universe. And when you have electric charge, for example, there are both positive charge objects and negative charge objects. Like a proton has positive charge and an electron has negative charge. But for gravity, for reasons that, well, I think we now know from our fundamental theory of physics, but hasn't really been known before, in gravity, you only have positive mass. That no negative mass exists. Now, people wondered, for example, when you have antimatter, the kind of the opposite charge version of particles. So an antiproton, which instead of having charge +1, has charge -1. People wondered until quite recently, until maybe 30 years ago, they wondered, would antimatter fall down towards the Earth like it has positive mass, or would it fall up because it has negative mass? Well, turns out antimatter falls down. So antimatter, like matter, has positive mass. And so far as we can tell, everything has positive mass. Actually, as I say, in our theory of physics, we kind of understand now why that would be the case. But actually, there's a little bit of a weird exception, which has already been thought about in the physics of the last 25 years or so, which is this idea of dark energy. And here's roughly how this works. So the question is, when you think there's nothing there in the universe, when you think you have a perfect vacuum, no particles, there's no atoms of hydrogen, there's just nothing. There's when you think there's nothing there, is it really the case that the vacuum has zero mass? And that's been a tricky thing in physics, because in the official theories of physics that have existed for 100 years, those theories, particularly the theory of quantum mechanics, says that the vacuum should actually have a non-zero mass. In fact, it should have a huge mass. In fact, in the vacuum, there should be these little funny quantum processes happening, so-called zero-point energy, and the zero-point energy should be absolutely huge. And it should be so huge that sort of everything in the universe should attract itself, and the universe should curl itself up into a little ball. And it's been quite unclear. I mean, for example, our theory kind of explains why that isn't the case, but it's been difficult to see that. But one of the other things that can happen is, independent of that, independent of the zero-point energy issue, there's also the question of, is there some kind of thing that we don't yet have a way to detect that will act as if it's a negative mass thing that's just spread throughout the universe? And one of the things that's observed in the universe is it seems that the universe, which is expanding, is accelerating just a little bit in its expansion. And one way that that acceleration could happen is if there was negative mass stuff in the universe. And so that is usually called dark energy. And so one of the possible theories is that there's something we can't detect it. It doesn't seem to interact much with anything that we can measure or anything like that. But maybe there's a little bit of negative mass spread throughout the universe. that actually has an interpretation in our models of physics that is basically this, when I talk about all this 0-point energy and all this activity in the vacuum and so on, in our models of physics, it's that activity that actually creates space in physics, that actually creates the possibility of saying there are two distinct points. There's something here, and you have to move to get to something here. That those things are not just all squashed together, that there's a notion of going a distance within the universe. And the thing that creates that notion of going a distance, that the thing that creates something like space is in fact precisely all of this activity that has been called 0-point energy. It's a little bit different than that, but it's that kind of idea. And in that setup, one of the weird things that can happen is most of the universe is just full of space doing its thing and being sort of knitted together by all these little processes that happen. And by the way, when we look at in our theory, we're not completely sure about this, but there's a question of the things that we are sensitive to, the things that sort of happen in space, the atoms and so on that exist in space, the protons, the electrons, all those kinds of things that exist. How important are those relative to the processes that just sort of knit together the structure of space? And at least in the current theory that we have, for every sort of thing that is creating like an electron or something, the amount of stuff that is just associated with maintaining the structure of space is, let's see, a trillion times larger. So a lot larger. So the vast majority of the activity in the universe is just maintaining the structure of space. And everything that we see that sort of happens in space is in a sense a tiny effect. But one of the weird things that can happen is maybe those effects can actually cause some of that activity that creates space to be a little less than it normally is. And if that happens, you end up with negative mass. But so that's a long answer to this question about can there be a place without gravity? The answer is, in the usual theory, it's like if you're away from all these masses, but you can imagine a different, much weirder situation where you have positive mass things and you have negative mass things. And you're kind of balancing those to end up with a zero mass situation where you don't have gravity. But right now we don't know how to do that. If we were trying to make an anti-gravity machine or something, then we would need that, but it's not clear that's possible. Oh, there was a question here about is negative mass possible, so I think I tried to answer that. Let's see. There's a question here. A question from Brian here. Do you think there's anything between the known particles and other elementary particles? So that's a little bit of a complicated question. So you know, remember atoms, as we know them, are sort of made of protons and neutrons in the nucleus and electrons, and protons and neutrons are made of quarks and gluons. And if we kind of drill down, what's inside what, the things where we don't know anything inside them are electrons, quarks, photons, particles of light. There are a few particles where, as far as current physics is concerned, we don't know anything about what's inside them, and they seem to be of zero size. Now, in our theory of physics, nothing is of zero size because space is made of these kind of discrete atoms of space. And so just like if you have some water, for example, and you say, I want a really tiny amount of water, you're gonna have a very careful, you're carefully measuring out water, and you want a really tiny amount of water. Okay, you have, say, I have like a milliliter, I have a microliter, I have a nanoliter. This is all, yeah, it's fine. I've got a little dropper, I can have that amount of water. But if you try and get a really tiny amount of water, you get stuck because at some point you're down to having only a few molecules of water. And at some point you say, I've just got one molecule. If I want even less water than one molecule, how do I do that? I can't have only part of a molecule, so to speak. And in our theory, the same is true in space. If you want to have really too small a distance, you eventually get stuck. There are no spaces discrete on that scale. You just can't go down to a smaller scale. And so when we look at things like particles, like electrons, the idea that an electron would be of zero size is not plausible in our models. In fact, in our models, an electron is probably, well, one estimate is it's, I mean, in scientific notation, it will be 10 to the minus 80th meters, roughly. That's, oh, let's see if I can do it. A trillion, 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 trillionth or something of a meter. So very tiny. By comparison, if in our theory an electron is 10 to the minus 81, let's say, meters across, by comparison, a proton is 10 to the minus 15 meters across. So a proton is huge compared to an electron. So for example, let's see, if we compare us to the size of the universe, for example, so let's say, let me just try and do this calculation, 10 to the 6. Yeah, so the difference in scale between us and the size of the whole universe is smaller than the difference in scale in our models between an electron and a proton. So in other words, if you were to sort of line us up end to end to go across the whole universe, it would take about 10 to the 26 people. If you were to line up electrons to go all the way across a proton, it would take, let's see if I can do my math properly, 10 to the 60, 10 to the 6, 10 to the 60, 10 to the 66 electrons you would have to line up. So immensely more electrons would have to be lined up one against the other to fill, to go across a proton than we humans, let's say a meter tall, give or take, would have to be lined up to go across the whole universe. So the electron is very, very tiny, but not of zero size. Okay, so the question then is, even below the size of an electron in our models, how much further is there to go? Well, in our model, there's about a billion trillion, compared to the elementary length, the shortest possible length, the electron would still be a billion trillion of those elementary lengths. So there's a lot of room to make something even smaller than an electron. And so whether such things exist, we don't know. Is it possible in our models that they exist? Absolutely. Could those things exist and be floating around the universe? Quite possibly. There's this thing called dark matter that exists in the universe, or seems to exist in the universe, and it's possible that that's what it is these particles that are very light compared to electrons, very small compared to electrons. I should explain what dark matter is. So I talked about gravity, and when we have a galaxy, for example, our galaxy has 100 billion stars in it, and our galaxy is slowly turning around. I think it turns around, oh my gosh, how long does it take? 100 million years maybe for the galaxy to turn once on its axis. But the galaxy it's a big sort of spiral shape. It's roughly flat, and it's a big spiral thing that slowly turns on its axis. Actually, the center of our galaxy has a big black hole, but it's slowly turning around there. Okay, so based on the laws of gravity, we can work out how fast the outer arms of our galaxy should be turning based on the number of stars that we see in our galaxy and based on the mass that exists in those stars. And we get the wrong answer. In fact, we get an answer that's wrong by a factor of 10. And so it seems like there's lots of other stuff in our galaxy that we're not seeing. And there are even situations like where two galaxies have gone through each other. They can do that, but there's enough sort of empty space. Very few stars will hit when two galaxies collide with each other, but some will. But there are cases like that where it seems like something is left behind where these galaxies collided that is being called dark matter. And there's a question of what dark matter is. I think it's possible that it's things we call oligons in our theory. There are many candidates for dark matter. One thing we know for sure is dark matter interacts very little with ordinary matter. And so people are interested in, can you do an experiment to find dark matter? Could you see whether you can get the dark matter to interact with this thing in this very special way? One of the hopes these days is the one thing we know for sure is dark matter has a gravitational effect, because that's how we're noticing that it exists, is because of the gravity that it produces. And so maybe, just maybe, something like the gravitational wave detectors that we have, something a little bit like that might maybe possibly be able to detect dark matter, but it's not clear. Let's see. There's a question here. Will technology allow for one true universal language for deaf, blind, Romance languages, Arabic, Asian, computer languages, eliminating the need for translation? Well, it's possible you asked the right person that question. So I have for a long time been interested in making computational languages where we can express in a way that computers can understand the kinds of things we want to talk about in language. And if you use Wolfram Alpha, which powers knowledge and things like Siri and Alexa and so on, if you ask it questions, you say, you know, what's the density of gold or something, or what's the caloric content of some kind of cookie? What does it do? It takes that natural language in English, let's say, it converts the question you're asking into its internal computational language, which will be something like the entity, the element entity gold, its property, density, et cetera, et cetera, et cetera. What is the value of that kind of thing? It converts it into this precise kind of symbolic computational language from which then the computer can go and get the answer, go and figure out the answer, compute the answer. So one of the things I've long been interested in is making a general language that can express anything you want to express in a computational way. I call that the symbolic discourse language. People actually, you know, the idea of doing this, it's an important thing, because if you want to, for example, if you're trying to explain to an AI, if you're trying to define for a self-driving car, what should its ethical principles be about, you know, when should it swerve to avoid this thing? When should it not? What should it do? You have to like tell it that in some form that is a little bit more general than just saying, if there's this patch of pixels in your camera, then do this. You have to make some principle about some kind of contract with it about what it should do. And the question is, how do you express that? And that's where this kind of idea of a computational language, a symbolic discourse language, comes in as a way of expressing that. Instead of writing a contract like people do, where it's written in kind of legalese, you know, a variant of English that's been made a little bit more precise, you write it in computational language. And there's kind of a question of, can you write everything? Could I do this conversation that we're now having in a computational language? And would that allow one to understand that more clearly, perhaps, than by expressing it in English? Well, one thing that's a little bit like that, but about 400 years old, is the idea of mathematical notation. I mean, I could say, let's add, 3 to 4, okay, and divide by 7. Okay, well, I can say that in words, but we know that I can write the notation 3 plus 4 / 7 or something. And that idea of using that sort of precise mathematical notation makes it a lot easier to express things mathematically. Same kind of thing can be done computationally. I've spent, about a third of a century trying to make sort of a computational language that can express lots of things computationally. That's been very successful and is used by lots and lots of people. But the thing that, so there's a question of that language can express all kinds of things, but there's still things it can't express. There are things about, for example, what I want to do. I want to eat a piece of chocolate. We have a pretty good representation of a piece of chocolate. Oh, it's 3 grams of milk chocolate of this type. But the I want to eat part, we don't have a good way to express that computationally, but I think it's possible to make one. And if we make that, then we will have a way to sort of turn a conversation into something that can be precisely specified, just like mathematical notation precisely specifies things. And where if you've agreed with somebody, this is how things are going to work, and you've written this computational contract, you can both go to that. And instead of having to ask somebody, is this contract, does it agree with what is going on or not? You can sort of just ask a computer and it can decide what's true. So this is an idea that I think is a very powerful idea, very important for a lot of things about the future of the world. a lot of things about the future of sort of telling AIs in general, artificial intelligences in general, what we want them to do, a lot of things about sort of the operation of the world and making sort of the transactions that go on more efficient and all those kinds of things, and defining things in a good way, and lots of different purposes, and resolving a bunch of issues about people's preferences and how you represent those and all those kinds of things. A lot of good purposes. So one question is, why hasn't anybody done this? Why hasn't anybody built this kind of symbolic discourse language? Well, fundamentally because it's hard. I mean, I've just spent a third of a century building the distance we've got so far, and we've kind of built this thing that's quite unique in the world and taken that amount of time to do. So first problem is it's hard. The second problem is people sort of have kind of thought it's impossible. Actually, the last time people didn't think it was impossible was in the 1600s. About 350 years ago or something. There were a whole bunch of people who tried to make what in those days they called philosophical languages, languages that would express meaning, but without having a particular language's words in them. So in those days, it was like, do you want to use English? Do you want to use Latin? No, let's use a philosophical language which can abstractly express things without having to have specific words. They were about 350 years too early. You couldn't really do it at that time. You didn't have computers. You didn't have a lot of other kinds of things. It didn't make as much sense then to do it. Now I think it does. Now, what can you not express that way? Well, one of the things that happens is if you say, I want to have a piece of chocolate, that's a statement. But if you say, I am most desirous of acquiring a piece of chocolate, or, I got to have that piece of chocolate right now. Those things translated into our symbolic language would probably be the entity that is me, wants to eat, the wants is a thing, eat is a thing, piece of chocolate. In other words, the sort of the nuance, the poetry of what I might say would be crushed out of it by turning it into this computational language. If what I care about is, well, did it happen? Did it not happen? Yeah, it's a great way to express that as a computational language. If I want to express sort of the feelings that I had in saying it and so on, well, I have to have another track to my computational language. I have to have, the emotion track to my computational language, which is a perfectly reasonable thing to have, actually perhaps even quite simple to do. But it is showing you that you're breaking meaning into this kind of collection of atoms that is a little different than the whole meaning packaged together in the way that we use it to communicate between us humans. So if the question is, can we ever get sort of a universal language where we can expect computers and AIs and humans and people who can only see things visually and can't hear sounds, or people who can only hear sounds and can't see things visually? Could we make something which can be adapted to all those different purposes? Absolutely, yes. Will it fully capture everything? Well, almost inevitably, no. The only way to fully capture everything is to have the thing itself, so to speak. And people often discuss, if you're making a translation of particularly something like a piece of poetry from one language to another, can you truly translate that poem? Well, the answer is no. You can translate certain slices of the meaning of the poem, but can you truly translate the whole thing? Inevitably, no, because inevitably there will be, like, for example, in language one, it might be that the word for a particular thing is ambiguous with three other words that are similar to it that mean other things, but that aren't really what the poem was talking about, but they're kind of a reference by using that word to things that are close to those other words. But in the language you're translating into, the space of meanings might be quite different. And the word, when you say, when you say, you say negatively about somebody, that person is kind of a toad. Well, in English, when you refer to toads in something, you might be suggesting that the thing you're referring to is bad in some way. But when you translate that into, pick a language, French, let's say, let's see. I don't know toad in French. Frog is grenouille, I think. But anyway, I have no idea what the nearby words are there, but I'm sure the meaning is not the same there. So in other words, you translate the word for toad, but you won't get that same kind of ambience of meaning that you would get in English. So in that sense, it's sort of translation is in principle impossible, but a level of translating meaning is absolutely possible. And I think this effort to make a symbolic discourse language, which I hope will be my next big project, once I've, quotes, finished figuring out the physics project, which is ending up having many, many tentacles where it's informing a lot of other kinds of fields as well. All right. Oh boy, so many questions. You guys ask so many things. There's a question from Anders here. This one I'm going to get myself in trouble by trying to answer, but the question was, who is the leader in information technology at the moment? And the person asking it says, my guess is China. That may be I mean, all I can say is that it's a funny thing when, you know, if you look at different things that are being invented, what kinds of things are being invented, what in different places, you know, different countries have been really big on, you know, this is a country that makes lots of cheese. This is a country that has amazing woolen products and so on. Different countries have different things they tend to specialize in. And even within information technology, there are countries that have sort of specialized and for which different areas are really a better fit. It's been a surprising thing in the software industry that most of the large software companies and most of the sort of most leading software companies have been in the US. Not necessarily started by people who grew up in the US, but they've been based in the US. And back when the computer industry was young, there were many countries like the Britain, other European countries, many countries where they were off to a good start. You know, Russia, another example. You know, they were off to a good start. They had computers. They were building, you know, they were building things. But for some reason, the sort of the center of mass of the software industry really moved to the US. And people have different explanations for this, having to do with the traditions of starting entrepreneurial companies where there's a lot of risk and so on. I think there's a variety of reasons, and maybe it gets us too far afield to talk about them. I mean, to me, the thing that's interesting in today's world is that I think with even technologies that we've built that try to automate a lot of the sort of stack of what you need to do computationally, there really isn't such a big advantage for a country that has developed a large sort of background in a particular area of information technology relative to other ones. And I think it's you know, it's becoming much more where there's a will to do it and where there's an interest in people really getting involved with the latest kinds of things, it's possible. It's not like a field where there is either physical resources, even factories that have been built, things like that, or know-how that is sort of uncatchable up by other countries, even quite small countries. And it'll be interesting to see how that develops. I'm always, we can get a little bit of an index of countries around the world if we look at our software, because we make a lot of software that's used for research and development and so on. And the amount, the level of usage of our software gives a pretty good indicator of how energetic research and development is in a particular country. It can be a little tricky because there are countries where people buy software like they do mostly in the US and so on. And there are countries where pretty much people just steal software. And so you have to kind of correct for that in making this estimate. But we have pretty good index of countries around the world, you know, and how kind of R&D sophisticated they are. But I'm going to get myself in I think that's a different topic here. Let's see. Oh boy. There's a question from Eduardo here about, is there a relationship between computational irreducibility and the uncertainty principle from quantum mechanics? It's going to take me too much time here to explain both of those ideas. the answer is not directly. In our models, computational irreducibility is associated with the progression of time. The uncertainty principle in quantum mechanics is associated with essentially curvature in what we call branchial space, which is the space of entangled quantum states. So they're a little bit, in order to get that second thing, you need computational irreducibility, but computational irreducibility is pretty much the origin of time. And that has a whole lot of other things that it brings with it. Let's see. There's a question here. Okay, there's a question here from Markup. Is there a formal definition of number? It's an interesting question. So, you know, what is a number? You say, there are three of something, you know, 3 fingers, whatever. One question that comes up is, are numbers necessary? If we were going to rebuild our civilization, or if we found some, you know, alien intelligence, would it necessarily have numbers? If you have a spaceship, do you necessarily have to have numbers? Well, it's an interesting question. You know, it's said that there are, you know, people living in the Amazon jungle who haven't had much contact or any contact with well, they have to have had some for people to know about them, but who have had very little contact with the outside world and who have languages that it's claimed don't really have words for numbers. Like our language has, you know, 1, 2, 3, 4, 5. We can count up to any number. We can specify, you know, 1,300,000, blah, 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 blah. We can say that number in our language. But it's said that in these languages, there's a word for a thing on its own, a word for a pair of things, and then there's a word for just lots of things. There's no notion of 1, 2, 3, 4, the notion of number that we have. So you might say, how could that possibly work? Well, it depends what you're doing. You know, if you have, you know, let's say you have a bunch of, what is there in the Amazon jungle? I don't know. A bunch of, I was going to say sheep, but I'm not completely sure there are sheep there. Let's assume there are sheep there. Let's say you have a bunch of sheep, and you know, you have a bunch of sheep, and you know that sheep is called Bertie, that sheep is called Billy, that sheep is called, you know, Jemima, that sheep is called whatever, right? And it's like, okay, so Billy and Jemima are off in that pasture, okay. But you're not saying 2 sheep are off there. When do you need to count sheep? When do you need to say all these things, which we currently just have explicit names for, are all the same kind of thing? Let's lump them all together and let's just count how many of them there are. Well, one time you start needing that is if you invent things like money and commerce. You might say, I'm going to trade you, you know, 3 sheep for 4 goats, let's say. Then you have to start, you know, having collective ways to refer to things, and you have to start inventing numbers. But it's, I think, not self-evident that you have to invent numbers for, you know, you can lead a perfectly satisfied life without inventing numbers, so to speak. Now, you know, if you look at the history of use of numbers in human civilization, people figured out whole numbers, integers, pretty early on. You know, you just make marks on a tally stick or something like that. Later on, by the time of the Babylonians, a couple of 4,000 years ago or something, people had figured out fractions. They'd figured out you can have 1/2, you could figure out 1/60th, you could figure out you could have these fractions. And they tended to want to represent numbers by, oh, and we have this number and such a number of 60ths. By the way, we still use 60ths because that's where our 60 seconds in a minute, 60 minutes in an hour, and so on comes from. That's from the Babylonians and their use of 60th fractions. Now, if you say, well, I want 1/57th, okay, well, so you can mathematically represent that roughly as, 1/60th plus something that's 1/3600th plus whatever. But there are numbers there are only certain numbers you can easily represent by fractions like that. So for example, the square root of 2, the number which when multiplied by itself gives you 2, can't be represented that way. So, normally if you say, okay, 9 is 3 times 3. 16 is 4 times 4. If we wanted to say what's 5 as a something times something, the something we'd have to put in there is the so-called square root of 5. Let's say we want to do that for 2. The square root of 2 is a number that's about 1.414. Multiply that up, you get 2. Multiply that number by itself, you get 2. But if you want to write down that number, if you wanted to write it down as a fraction, it would go on forever. Okay, so the idea of representing numbers in terms of fractions, that was known 4,000 years ago. The idea of doing what we do today, writing down numbers as decimals, where I could say 1.4142758 whatever, however it goes, that idea of writing things in terms of decimals, in terms of a sequence of numbers like that, a sequence of a place value sequence where you've got things that are a tenth, things that are a hundredth, things that are a thousandth, et cetera, et cetera, et cetera, and having that go on forever. That idea is quite new. I mean, that idea, by quite new, I mean it's 400 years old, but on the scale of understanding of mathematics and of civilization, it's quite a new idea. And this idea that there are, that you can make a number where you can have all these digits. Okay, so one question is, if I pick a value, can I write down a number that corresponds to that value, whatever value I pick? It's very similar to the things that I was talking about with space, where if you pick a point in space, can you pick any point you want? Or is there a discrete kind of structure of just, well, you can pick that point, but the next neighboring point a little distance away? So with numbers, there's this question of, can you pick just an arbitrary number, or are there only a discrete set of possible numbers, even if they're very, very close together? Now, you could ask the question for physics, are there sort of an infinitely close collection of numbers that can be implemented in positions in space, for example? But you can just ask mathematically, can there be just numbers that are arbitrarily close together? So in mathematics, the idea that there can be numbers arbitrarily close together, yep, standard modern mathematics says, yes, there absolutely can be numbers that are arbitrarily close together, a so-called continuum of numbers, the so-called real numbers, as opposed to integers. The real numbers can be infinitely close together. Now, what can you do with numbers that are infinitely close together? Well, it's kind of a mess. For example, when you write programs for computers, you always have to make numbers that have only a limited number of digits, or they're kind of a little bit like integers, or a fixed length of fraction or something like that. Computers only deal with sort of discrete numbers. They don't deal directly with these continuous real numbers. You can just say, I'm going to have a thing called x, and it's going to represent one of these real numbers. Like you can say x times x equals 2. So x is the square root of 2 number, but it's a more tricky thing to say whether to characterize that. Now, so here are some tricky questions in mathematics. So if you just say, let's count the number of possible integers, number of possible whole numbers. You say, well, that's infinity. Okay, well, there was a chap called Georg Cantor about 100 and a bit years ago who had this way of classifying different kinds of infinity. He had these things he called transfinite numbers. And so in his world, the number of integers is a number called Aleph 0. It's named after a letter of the Hebrew alphabet. So in his way of saying, well, there's an infinite number of whole numbers, but we're just going to call that infinite number of whole numbers Aleph 0. Okay, so then there's the question of, well, what about the real numbers? How many real numbers are there? Well, he said the real number of real numbers is Aleph 1. Okay, so then it's a little bit of a tricky construction, but you can kind of ask the question. I don't think I can, it would take me a few minutes to explain this, but basically 2 raised to the power of LF0, there's a pretty good argument that 2 to the LF0 should be equal to LF1. That is, that if you take sort of the number of integers and you take that and you say 2 to the power of that infinite number, you get this other infinite number. That's the number of real numbers. There's sort of an argument for why that should be true. Okay, awkward fact in mathematics. Mathematics, as it's normally set up with the normal rules for mathematics, where we know what we think we mean by integers and we know what we think we mean by numbers and so on, those ordinary rules for mathematics don't tell you if that's true, that 2 to the LF0 is equal to LF1. It's called the continuum hypothesis. And the continuum hypothesis is kind of interesting because it is a hypothesis that you can either say it's true or it's not true, and you get 2 different kinds of mathematics depending on which one you say. And so people often talk about ZFC as a set of axioms for mathematics that include the continuum hypothesis, but you can also make axioms for mathematics that don't include the continuum hypothesis, and those correspond to, you get a sort of a different set of mathematical conclusions. So it's a very tricky thing when you start thinking about, you know, the questions like what is the number of all possible numbers and things like this. Actually, to zoom ahead to something that this relates to kind of the meta-mathematics of sort of all possible mathematical results. And in some sense, we can think about the space of all possible mathematical results as being a little bit like the space of all possible positions in the physical universe. And we can actually do science on that space of possible mathematical results, a little bit like the science that we do about the physical universe. And one of the bizarre results that we've just been working on the last week is that it looks like the continuum hypothesis can be thought of as the analog of a black hole in meta-mathematical space, not in the physical space of our actual universe, but in this abstract meta-mathematical space. So that's something very bizarre. But the general notion of a number, it's a complicated notion. And you know, when you start really generalizing it and start talking about the transfinite numbers and things like this, it's a complicated notion. I have a feeling actually that some of the things we've recently been doing about the analogies between mathematics and physics might actually give one, actually a good point, might actually give one a way to think about the most general conceivable thing that might be thought of as being like a number. I mean, in a sense, a number, actually, there's an interesting point. I should remember this point because I'm about to think about this stuff. This way of condensing, you know, all these different sheep and just saying, oh, there's 7 sheep. That way of saying all that matters is the answer for how many sheep there are, and the details of each sheep don't matter. That, I think, is probably bizarrely similar to various kinds of foundational axioms in mathematics that are what lead one to be able to do mathematics, which have an analogy to the things that let one be able to do physics in the physical world. But we're ascending into a ridiculous level of abstraction, which I'm hoping to actually understand better even in the next few days. Let's see. All right, there's some. Okay, there's a question. Oh boy, there's all kinds of interesting questions here. There's a question from Kunal. Why are all electrons the same? Good question. We think we know the answer. Well, actually, they're not all the same. They have, for example, they have different momenta and different energies. There's an electron that can be going much faster, an electron that's going slower. But what we think is that it's kind of like when you have a knot in a piece of string. The knot has some particular form, and you can move the string around a bit, but still the knot, the structure of that knot can stay the same. The topology of that knot will stay the same, even though you move little pieces of string around a bit. And I think it's kind of the same thing going on inside an electron in our theory of physics. It's kind of like there's this sort of almost topological, this sort of thing that's kind of a little bit like a knot that is the core of the electron, that is what makes the thing that you have be an electron rather than not an electron. But there's also things like how fast the electron is going, and that's not associated with that sort of core knot. That's more associated with the actual way that the knot is kind of laid out in the universe and so on. But I think the reason that all electrons are the same is because it's like saying, well, you've got all these pieces of string and you've knotted them somehow. There are only a limited number of ways that you can make a knot with a certain number of crossings or something like that. And that's kind of the reason that all electrons are the same. It's almost sort of a mathematical reason. More elaborately, well, let's say that's a good first cut. My friend Richard Feynman, physicist, he and his thesis advisor a long time ago in the 1930s and 40s actually, they were debating this question about why are all electrons the same? And they had a really weird idea. Their idea was, actually, there's only one electron in the whole universe, but that electron goes forward in time, then back in time, then forward in time. The back in time version is a positron, the forward in time version is an electron. That theory turns out not to be true, but it's kind of an amusing theory of the reason all electrons are the same is because there's only one electron. It just keeps zipping back and forth in time. That theory isn't correct, but there are different reasons now. Okay, a couple of questions here. What temperature does a laser have? Okay, tricky question. All right, so what is temperature? So temperature, when you heat something up, what's happening? What's happening is that the atoms or molecules in the thing are going faster and faster. The atoms and molecules have more and more energy running around. So when you heat something up, the temperature is the average energy of each thing, like atom or molecule, in the thing you're heating up. And when that average energy, which determines how fast the things are going, gets big enough, for example, if you have a solid object, the things will be running around so quickly that the solid object will turn into a liquid, or they'll be running around even faster and it'll turn into a gas. But so what temperature measures is the average, the average energy of like atoms, molecules in a thing, okay? Well, there's another little piece of trickiness, which is when a thing is in thermal equilibrium, that means its temperature is no longer changing. It doesn't have it might be cold at one end and hot at the other, but eventually it will equalize and all be at the same temperature. That's thermal equilibrium. When you get to thermal equilibrium, what happens is that on average, the atoms, let's say, in the thing will have a certain energy, but not every atom will have precisely that energy. Instead, there will be a distribution of energies that is actually an exponential distribution, e to the minus energy divided by temperature, E of a kT, Boltzmann's constant times temperature. And so what that's saying is that the chance that you have an atom with a certain temperature, with a certain energy, rapidly decays. So you have more atoms with lower energies, fewer atoms with higher energies, and I'm leaving out the full version for people who care about this in classical physics. Ignoring quantum mechanics is a thing called the Maxwell-Boltzmann distribution, and that has it's of the form, if you look at the velocity of particles in a gas, at least, it's proportional roughly. If the velocity is v, it's a v squared times e to the minus v squared. Is the distribution. But anyway, all right. So, but the main point is that things running around, molecules that are running around faster have, there's a lower chance to have a molecule that's running around faster at a given temperature with normal positive temperatures. Okay. Okay. So what happens in a laser? Let's see. All right. The end result of this story is going to be that lasers effectively have negative temperature. But let me try and explain that. So so what I've said is that normally the energy of atoms decreases with the probability that you have an atom of a certain energy decreases with that energy. Okay, how does a laser work? Oh, this is tricky. Okay, so first of all, what does the word laser stand for? It stands for light amplification by stimulated emission of radiation. And the idea of how a laser works actually was kind of a footnote to work that Albert Einstein did on photons and on the idea of how photons work. Photons are particles of light. Originally, it was a footnote. By 1960, people have realized it was more than a footnote, and they invented lasers. But here's the footnote. The footnote was to say that particles that are so-called Bose-Einstein particles, and there's an Indian physicist, oh, what's his first name? Anyway, his last name was Bose, who also invented this idea. The idea is particles like photons, unlike particles like electrons, photons really like to be at the same energy and be in the same state. And if you have a photon and you have something like an atom that is going to emit a photon, then if you have an atom that's going to emit a photon, and there's already a photon out there that is at the same energy as the photon that atom was going to emit, the chance that the atom emits the photon will be higher. In other words, it's more likely that the atom will produce a photon if the photon is going to meet a friend with the same energy, so to speak. The exact opposite thing happens with electrons. With electrons, they have a thing called the exclusion principle, which says if there's already an electron with that exact same energy, you just can't put another electron there. Okay, but with photons, it's the other way around. Photons like to get together, and the chance that you emit a photon increases with the number of photons that are already there. Okay, so what happens in a laser is basically that you are using hell, this is going to get tricky. Essentially, what you're doing is you're setting things up so that you are going to have lots of photons all in the same state. And those ones all in the same state, they all have the same energy, they're all the same color, they're all going in the same direction. That's how you get this coherent beam of laser light. But the way you get that is through a process called pumping, which is a process where you basically are inverting you're making there be more atoms that have higher energy than have lower energy. That's the opposite of what you would have with positive temperature. You would have it the other way around. But in a laser, you're effectively trying to have more atoms with a higher energy and fewer atoms with a lower energy. And then what happens is the atoms with a higher energy, they all sort of want to emit a photon, and they're all the photons they want to emit, they're all going to emit the same photons with the same energy going in the same direction. You arrange it that way. And they all kind of want to get together to do even more of that. And that's what the light amplification by stimulated emission, that's what this process of sort of them all wanting to throw photons together is about. So basically, one can say that in a laser, roughly one can say that the atoms that are emitting the photons there are essentially have a negative temperature. It's not really temperature in the ordinary sense, because if you were to just say, okay, I don't want to have, I'm pumping this with an electric field or with electricity in some way to keep it in this weird inverted state. If I got rid of that pumping force, it would just go back and it would go into thermal equilibrium and it would have positive temperature just like everything else. But if you keep kind of pumping it into this inverted state, you can maintain this kind of effectively negative temperature, and that's kind of how lasers work. let's see. I need to, let me, oh gosh, there are a lot of interesting things. Let me try and just do a few more of these and then I need to go. I just want to make one kind of comment for, I mean, this, I should say two things. First of all, these Q&A live streams are primarily intended to be about general science, technology, other things. I kind of started doing them because we're in the middle of a pandemic and I thought kids who weren't in school might find this kind of stuff interesting. I think so these are kind of, I'm trying to explain things at a sort of, at a level where I hope kids are finding it interesting and are understanding what I'm talking about. There's also things to say about our physics project where I can talk at a much, much, much higher level about, it's like, assume you have a PhD in physics, then I can tell you this, this, and this. But that's sort of a different branch of what I'm trying to do here. I do want to say that I have for years in person, where I live in Massachusetts, been doing sort of every week, before there was a pandemic, I was doing it in person, kind of a thing with kids, which originally is mostly talking about programming and making computers do things, but particularly as we've gone pandemic and virtual, has ended up being kind of about thinking about things in general and understanding how the world works and about science and technology and other things. And since it's all gone virtual, I have the potential to have other kids involved in that. And it's primarily, I would say, I've got two groups. One is kind of age-ish, 10 to 12-ish. Another is more like 13 to 16-ish. I guess if there are kids who fall into those categories who are interested, I'm going to be sort of opening up my Zoom sessions, at least during this pandemic time, to other kids, and you should get in touch with us. How would you get in touch with us? I don't know how you get in touch with us. I think you send a private message in this live stream chat, or you send email or something. That's terrible. I don't really know, oh, okay. They can email outreach@wolfram.com if people are interested. Okay, I'm just going to do a couple more questions here. Question from Anders: how do galaxies retain their shape for billions of years? That is a somewhat good question. It is not as well understood as you might think. So our galaxy, which is a pretty big galaxy, is a spiral galaxy. It's pretty flat, a little bit like our solar system is pretty flat. The planets in our solar system are roughly all orbiting in one plane. There's not like Pluto, which isn't viewed as a planet these days, is a little bit out of the plane of the ecliptic, the plane defined by the orbit of the Earth going around the sun. But mostly planets are in this flat plane, probably because when they formed, there was this big dust cloud that was sort of spiraling around the star that was forming, and they all kind of squashed down through the force of gravity into this kind of flat plane. And that's probably also what happens in our galaxy, that it all sort of squashed down, all those 100 billion stars in our galaxy kind of squashed down into this more or less flat plane of our spiral galaxy. Now, there are other galaxies, like there are galaxies that orbit our galaxy, galaxies called the Magellanic Clouds, that are smaller. They have maybe 10 million stars in them, I think. And those galaxies aren't flattened out. Those galaxies are still kind of spherical. Now, these big galaxies like ours that are spiral galaxies, they're flat collections of stars, and they form these spiral arms. They form arms that sort of concentrate the galaxies into this kind of spiral shape. And exactly how those spirals are formed and maintained is difficult to understand. And there are a bunch of theories about that. I think by now, well, people who've tried to simulate what happens if you have 100 million, a billion stars. It's hard to do a billion, but if you do a bunch of stars on a computer, you just say all these stars are moving according to the laws of gravity. They all have this inverse square law force between them. Just work out where these stars will go based on starting in a particular way. Well, people tend to find, I think, they now find they can find the formation of spiral arms. But why those things don't fall apart and whether you can tell how old a galaxy is by how delineated its spiral arms are, I'm not sure. I think there were theories about that at one point. There are theories about, there are theories about kind of waves of star formation and waves of supernovas and things like this. I don't know that in total detail. I knew the state of that probably 25 or 30 years ago, but I think it's advanced since then. So I'm not able to give you absolutely the latest information, but I think it's still a bit mysterious why the shapes get maintained the way that they do. There was a question here. There's a statement here from Lefob. It will be really interesting to observe the effect of a logic-based language on the cognitive development of children. Yeah, that's an interesting issue. There's this whole question about whether the language that you use determines the way you think about things. People have argued about that a lot for human language. There's a thing usually called the Sapir-Whorf hypothesis that says the language that you use to describe things determines how you think about things. And the famous example is, Eskimo peoples have many words for snow, whereas those of us who don't live in places where there's lots of snow just have the word snow for snow. And, it's hard to talk about, oh, it's a fluffy kind of snow, it's a flaky kind of snow, whatever, if you just have one word for snow. And people say that, for example, in some languages in antiquity, there was not a different word for green as for blue. And so there are questions of whether, and so that caused people to have different descriptions of things. I think there is some effect of the words that you have in a language determine how you think about things. Certainly, for example, if I say I'm writing a blog or I'm doing a video conference, if I had, both of those things I sort of did long before there were words for them. But explaining what I was doing was quite difficult without a word. So, having that word, it's like a video conference. Okay, we know what that means. So, I think that there's a certain sense in which words help crystallize concepts so that we can explain them. In computational languages, the effect is much greater. Like in our Wolfram language, we've tried to sort of condense a bunch of computational ideas, and that I would say, dramatically affects the way that people think about things computationally. And it's kind of, for me, it's been very interesting because as the designer of this language, I mean, human languages like English don't have designers, but computational languages do have designers, and the way that one designs the language affects how people think about things, and that's pretty interesting. So there are artificial languages people have made, probably two particularly notable ones to me. Well, there's one historical one that's notable, Esperanto, made in the 1880s, which was an artificial language kind of modeled after some European languages. It's a language that has a simple grammar, it's phonetically spelled, it's sort of a simplified language. And maybe 1 million books have been written in it, I think. And it's had gotten some distance. I was very sad many years ago when I saw the European airports. They used to have signs in a bunch of different languages for the different European languages, and then they'd have a sign in Esperanto. And I was kind of sad when the Esperanto signs disappeared. I thought that was kind of the end of an era for that. But there have been more recently, there have been languages that have been made with different purposes. I would say some of the languages that get made for television shows, like, Game of Thrones has its very own language called Dothraki. I'm sorry to say I can't claim to have watched that show for more than 5 minutes, but I watched it mainly to see the Dothraki language. In any case, there are other, or Klingon in Star Trek is another artificial language that was made kind of for artistic purposes. There are other ones that have been made for slightly more practical purposes. There are sort of two extreme examples, which are kind of interesting. One called Ithquil and one called Tokipona. So Tokipona is a language that wants to be as minimal as possible, and it only has 150 words. And the idea is that you should be able to express yourself with only 150 words. I mean, in English, we have maybe 30,000 words that we often use. But can you do it in 150 words? Not clear. I haven't really tried speaking Tokipona, so I don't really know. But that's one. Ithquil is the exact opposite. Ithquil wants to put every concept for every human language in. So, for example, in English, we have, the present tense. I talk. The future, I will talk. Perfect, I have talked. Aorist, I talked, etc., etc., etc. All these different tenses of verbs. Ithquil has sort of a collection of all tenses of verbs that are found in sort of more or less all the languages of Earth, and I think it has, 50 tenses or something. So it's attempting to put all of the stuff one can into this language. And so then the question is, well, first of all, I can say that the creator of that language is not a fluent speaker of the language. So that's kind of gives you some sense of the level of sophistication necessary to have all of these concepts from all these different languages and so on, all bundled together in one language and talk in terms of that language. There have been people who've tried to sort of improve themselves intellectually by sort of learning to speak that language as a way to kind of sort of have more intellectual horsepower. Unfortunately, from what I gather, the particular people who've been most involved in that have many other bizarre problems. And so that the experiment isn't a very good one. But I don't know, if you taught a kid Ithquil, what would happen? I don't know. I think I knew one person once whose first language had been Esperanto. He was a bit odd. But I think that I don't know whether that was cause or effect, partly because in an environment where one's parents choose to teach one Esperanto as one's first language, that's an unusual choice, let's say. There's a question here, will it be possible to tell, from Brian, will it be possible to tell a joke in a symbolic discourse language? Who and what may find it funny? That's a funny question. I think, interesting question. That sort of relates to what are jokes. And, we were interested in the kind of computational creation of humor. Like we wanted to have something where you could ask Wolfram Alpha, tell me a joke about a cat and an elephant. And it would find some, maybe it's a pun, maybe it's a this, maybe it's a that. What is, given a seed, can you tell a joke about that thing? And I think, there are various theories about sort of the role of jokes and what and how, how jokes sort of relate to thinking and so on. And I think, this question of whether there's a sort of formulaic way to create computational humor, I kind of have the suspicion that for puns, wordplay type things, there probably is a somewhat formulaic way to do it. Which ones will be truly funny depends on their long tentacles of meaning stretching out into other things. And really, they're in the same way that poetry sort of has these long tentacles of meaning coming out of words. I suspect you have to have the same type of thing go on. And, the next question is, could an AI find something funny? That's a good question. I have to think about that. I mean, the answer, can it have the same behavior as we have upon finding something funny? Of course. Is there some intrinsic notion of an AI finding something funny? That's an interesting question. In other words, what is the formal computational definition of a joke? Just like we can have a formal computational definition of meaning, can we have a formal computational definition of a joke? We can probably have a formal computational definition of a pun. That's pretty easy. In fact, the minimal form of puns we experience every day, because when we take the feed of things that started as spoken language in an intelligent assistant like Siri or Alexa, and they get fed into our Wolfram Alpha system, the first thing that has to happen is you have to have conversion from the natural language as spoken to something which can be a written language which is converted to the symbolic form. And so regularly something like pi, pi, the mathematical thing, pi equals, circumference to diameter of a circle, 3.14, et cetera, et cetera, et cetera. That's spelled pi, but it's said the same in English as pi, PIE, the word for, a thing you eat. And actually, I do have to tell a story, which is actually relates to the, I think the person who's managing this live stream today, who works on events at our company. A number of years ago, it was Pi Day of the century, the day where in American dates it was 3.14.15. So March 14th, 2015, just like the digits of pi, 3.1415. And we were going to do an event at a big trade show in Austin, Texas. We were going to do an event on Pi Day. And I was like rather offhandedly saying, what should we do for this event? Oh, we should get a big pie. And the person who was organizing this event was like, she said, came back in some other meeting, we've looked for pie baking places in Austin, Texas, and we really can't find one that can produce, that big a pie. And it's like, what on earth are you talking about? I was, when I said pi, I meant pi, the mathematical thing. And I was imagining that we'd have this big, wooden object that was in the shape of a pi symbol, not a pie that you could eat. As it turned out, at the actual event, we had both, just to cover base as well. But that's a sort of an example of a pun in action, and the kind of thing we see, 100,000 times a day in the kind of things that go from natural language to written language to computational language. Okay, I think I probably should. There's just a couple of quick ones here. There's a from Cluey saying, I once said that long ago, Richard Feynman gave me a collection of mathematical tricks for integration, which I didn't use. Have you published them? And the person is saying they'd really like to see his notes. No, I never published them. They're sitting in a file cabinet somewhere. And I am working towards putting on the web a large collection of archival material, of which that will definitely be one. And I kind of feel bad because there's a bunch of notes that Dick Feynman, one day he said to me, here's all these notes about how to do these various kinds of calculations. Let me lend them to you. He'd written them in the 1950s, I think. This was probably around 1980 or something that he gave them to me. And I'm like, oh, sure, I'll borrow these. Well, that borrowing started in 1980 and I still have them today. So I think I should put them on the web. I just haven't gotten around to it. All right, well, I should wrap up here. Actually, I'm being pointed out that I wrote a post about Dick Feynman that has pictures of a few of those pages of notes that he gave me. All right, well, thanks for coming, everyone. And I look forward to continuing this another time. Thanks for great questions. See you another time.